you guys? I hope you're having a good weekend so far. It's probably Sunday for you if you're catching this right when I've uploaded it. So welcome back to another video. This time I have for you a science kind of fact video. I found this article on a science website. I actually subscribed for $1. I think I get about 6 weeks. So I'll try to read a few of these if you like them. This one is called 10 Mysteries That Physics Can't Answer Yet. It's broken down into like 10 articles. So the first one is, what came before the Big Bang? Has the universe existed forever, or was there something before it? To find out, we need a working theory of quantum gravity and a new conception of time. Pause, rewind. Suddenly, the outward rush of 200 billion galaxies slips into reverse. Instead of expanding at pace, the universe is now imploding like a deflating balloon, faster and faster, smaller and smaller. Everything hurtling together until the entire cosmos is squeezed into an inconceivably hot, dense pinprick. Then, the screen goes dead. According to the Big Bang Theory, our best explanation for why space is expanding, everything exploded from nothing about 13.8 billion years ago. Cosmologists have been able to wind things back to within a tiny fraction of a second of this moment, but now they're stuck. The trouble is, our understanding of space-time, and gravity in particular, is built from Einstein's equations of general relativity, whereas the extreme conditions of the very early universe can only be described by quantum mechanics. No one knows how to reconcile the two to take us further back. The rules we have simply don't work in that regime, says Carlo Contaldi at Imperial College London. Nothing makes sense anymore. That's a problem for our origin story. Did time begin with the Big Bang, or was there an epoch before it? Some insist that if we rewind the universe far enough, time just stops. But Lee Smolin of the Perimeter Institute for Theoretical Physics in Waterloo, Canada, is having none of it. It's a cute idea, but there's not much evidence for it, he says. In fact, Smolin wants to see the idea that the universe has a starting point dropped entirely. We can only hope to explain why our universe is the way it is, he says, if there was something before the Big Bang. It's about cause and effect. To arrive at satisfying explanations for why things are as they are, we draw on previous events that led to the conditions we see. One possibility is that instead of a bang, there was a bounce. In this scenario, rewinding our universe would not take us back to a point containing infinite mass in an infinitely small space. Instead, it would take us through the unimaginably hot, dense beginning of our universe, and out the other side into the unimaginably hot, dense ending of a previous universe. Acknowledging that something came before the Big Bang would open the door to explanations of how the universe came to be just right for life. Otherwise, we either have to accept that our perfectly crafted universe was just a fluke, or that it is one of an infinite number of universes, most of which look very different, and we only think of it as special because we're in it. Or perhaps our Big Bang was one of many. Some think our universe popped into existence as a bubble in a frothing sea of universes. This idea gives our universe a beginning but introduces an everlasting multiverse. Can we ever really know? Small in things we could soon see clues in the cosmic microwave background, radiation given off by the early universe. It's possible that ripples in space-time known as gravitational waves might also survive a bounce. Cataldi is not holding his breath. We need a working theory of quantum gravity, and a new understanding of time, he says. Without that, I don't think we have the tools to even pose the question properly. So that was kind of a deep one. But the next one is a little less existential. It is, how does a bicycle stay upright? Some of these things might be a little surprising to us non-scientists. Like, I didn't know that scientists didn't know how a bike stands upright. Well, I guess we're not going to find out. So. We thought we knew the maths behind cycling. We were wrong, and our efforts to figure it out are leading to some weird and wonderful new bike designs. In 2011, an international team of bipedal enthusiasts dropped the bombshell that, despite 150 years of analysis, no one knows how a bicycle stays upright. Across the world, riders dismounted and stared at their bikes in disbelief. What they had been doing for years was a feat inexplicable by science. Well, sort of. What we don't know are the simple, necessary, or sufficient conditions for a bicycle to be self-stable. Necessary or sufficient conditions for a bicycle to be self-stable, says Andy Ruiner, an engineer at Cornell University in Ithaca, New York. We've relied on trial and error engineering to construct stable bikes that aren't prone to toppling while in motion. Explaining how they work mathematically requires around 25 variables, such as the angle of the front forks relative to the road, weight distribution, and wheel size. Before 2011, researchers had reduced this profusion to two things. One was the size of the trail, the distance between where the front wheel touches the road and where a straight line through the forks would meet the ground. The other was the gyroscopic restoring force that acts on a spinning wheel to keep it upright. Ruiner, I'm probably saying his name wrong. Ruiner and his colleagues, including Aaron Schwab of the Delft University of Technology in the Netherlands, and Jim Papadopoulos of the University of Wisconsin Stout at Menominee. I've never heard of that place. Not only revisited this mathematics, but also skewed the trail and gyroscopic forces in prototype bikes to make them technically unrideable. To everyone's surprise, the bikes were still stable. The researchers haven't been resting on their saddles since. Last year, Ruiner unveiled a bicycle, a cross between a bicycle and a tricycle, with spring-loaded stabilizing wheels that can be adjusted to vary the rider's perception of contact with the ground. By studying the influence this has on how the rider steers and remains stable, he hopes to gain new insights that might lead to more easily controllable bicycles. It's still an uphill struggle. I think the real understanding of bikes requires a mix of what we did plus some kind of brain science, says Papadopoulos. Human riders act in extremely complex yet intuitive ways to keep a bike balanced and on track. At very low speeds, for example, we recognize that the handlebars become useless for steering and instead direct the bike by wobbling our knees. Why, we don't know, says Schwab. Yet another bike-based mystery that could be around long after we've worked out the origins of the universe. Does that one surprise you? There's still some even more random ones coming than this. Here's another one that's more about the universe. This one's called, Is the Universe Infinite or Just Very Big? I've always heard that it's infinite, but it sort of never made sense to me how that was possible. Again, we're not going to find out the answer in this article. So, the size of the observable universe is easy enough to measure, but what lies beyond the cosmic horizon? We have a long way to go to find out. Just to put things into perspective, this article was written in 2015, so maybe we're not as far off of finding things out now that AI is so close to taking over. We've known the size of Earth since the time of the ancient Greeks. The Sun, solar system, and Milky Way, no problem. But when it comes to the size of the universe, we haven't got a clue. It's weird. The size of the observable universe is one of the more precisely known quantities in astronomy, but the size of the whole universe is one of the least well known, says Scott Doddleson, a cosmologist at Fermilab in Illinois. One way to think about the size of the observable universe is to consider how far light emitted at the Big Bang could have travelled by now. According to our best cosmological models, the distance is about 46 billion light years. This is the cosmic horizon, a sort of three-dimensional equivalent of the 2D horizon we see on Earth. That is as far as we can see and how big, empirically, we can observe the universe to be, says Adam Rees of Johns Hopkins University in Baltimore, Maryland, who shared the Nobel Prize in 2011 for the discovery that the universe's expansion is accelerating. Of course, we are pretty sure it goes out much farther. Why? Because the universe looks very similar no matter which way you look. Take the cosmic microwave background, or CMB, the radiation left behind by the Big Bang. It's largely uniform across the sky, and we have no reason to think that would change beyond the cosmic horizon. There are no signs the universe is tailing off, so it would be a surprise if it abruptly ended. Daniel Essenstein of the Harvard-Smithsonian Center for Astrophysics says that if the universe is only a little bit larger than what we see, we might expect to find hints of structures much larger than galaxy filaments, formations of superclusters of galaxies. These hints would show up as wild variations in the temperature map of the CMB, the cosmic microwave background. But they don't, which implies that the universe is much larger than our little observable corner. If that's the case, Essenstein says it will be a struggle to figure out how big it is. It might be 1,000,000 times larger, or 1,000,000,000,000, or even infinite. A truly infinite universe might be tough for us to comprehend. Particularly perplexing is the idea that if the universe is infinite now, then it must have always been so, even during the earliest moments in its history when the distances between objects were much smaller. But we would have to go a long way to rule it out. Okay, so number 4 is, how long does a proton live? They are the essential heart of every atom, so it's just as well we've never seen a proton fall apart. But they can't live forever, can they? The Bible of Fundamental Physics, the Review of Particle Physics, devotes several pages to the ways a proton might fall apart. Each decay mode comes with an estimate of how long you might expect to wait to see one of these particles, bedrocks of the atomic nucleus, disintegrate that way. The units are thousands of billions of billions of billions of years. Our stripling universe is a mere 13.8 billion years old. So this is a judicious, scientific way of saying that no one has ever seen a proton decay. It's not for want of looking. A 50,000-ton tub of ultra-pure water under a mountain in central Japan is one place where researchers are watching out for the pop and fizzle of a dying proton. Late last year, the team published, this is another one that was done in 2015, Late last year, the team published its latest estimate for how often one particularly eagerly sought decay mode occurs. At most once every 5.9 times 10 to the power of 33 years. You'd think people would be pleased that the particles we're all made of are stable. Physicists too. Their standard model of particle interactions firmly indicates that protons, as the lightest particles constructed of 3 quarks, should never decay. So why is never not good enough? The answer is that few believe the functional but ramshackle standard model is up to snuff. So-called grand unified theories provide a more coherent account of 3 of nature's forces. Gravity remains aloof at the price of the proton decaying. It's the signal of the grand unified theory, says Benjamin Alanak, a theorist at the University of Cambridge. Not only that, but these ambitious models predict the proton should live for somewhere between 10 to the power of 30 and 10 to the power of 35 years, just the range experiments are now probing. We're entering the really interesting area where you can start to rule these theories out, says Alanak. Or if they're correct, you should start seeing protons decay. It could be a long wait. Pushing the minimum lifetime up to a factor of 10 means watching for 10 times as long. So should we be worried if one of the fundamental components of matter, the stuff that makes up you and me, proves to be a little wobbly? Not really. Our bodies do not make good observatories for proton decay. From my back of the envelope calculation, it would be a rare person that would experience a proton decay in their lifetime, says Alanak, and the universe has so many protons that will be long gone before they run out. In the meantime, here's the best answer we have for the lifetime of a proton: a very, very long time. So this next one: why is ice slippery? Most think it's down to a liquid layer, but can't agree on how it forms. One theory insists it's a super solid skin capable of electrostatic repulsion. For physicists, no less than figure skaters, ice is remarkably hard to get a grip on. The overwhelming consensus is that ice has low friction because of a thin film of liquid water coating its surface. Hence, skaters balanced on thin metal blades can glide smoothly across the ice rink, but grind to a halt on the wooden floor beyond. The tricky part is how this liquid layer forms. More than a century of research has brought us little closer to the definitive answer. It all started in June 1850, when Michael Faraday told an audience at London's Royal Institution of how pressing 2 ice cubes together led to them forming a single block. He attributed this to the appearance of an intervening film of water that quickly refreezes. For many years, the appearance of this layer of water was put down to pressure. In fact, even a person of above average weight on a single skate generates far too little pressure to account for the observed melting, says Anne-Marie Kietzig of McGill University in Montreal, Canada. The mathematics doesn't work out. Instead, Kietzig argues that the main player is frictional heating. The movement of a blade across the ice, for instance, easily generates enough heat to melt some of it. You might think that would be the end of it, but Chungking Sun of Nanyang Technical University in Singapore has other ideas. He argues that since ice is slippery even when you're standing still, friction cannot be the whole story. Mechanisms such as friction heating and pressure melting have been ruled out, he says. According to Sun, the assumption that the slippery layer coating ice is a liquid is also fundamentally flawed. He says this layer should probably be called a supersolid skin, because the weak bonds between H2O molecules at the surface are stretched. But unlike in liquid water, none of them are broken. He also argues that this elongation of bonds ultimately produces a repulsive electrostatic force between the surface layer and anything it comes into contact with. He compares the effect to the electromagnetic force that levitates maglev trains. What is that? I think they're just fast-moving trains. Maglev trains, or the air pressure a hovercraft generates beneath its hull. If he's right, his model helps to explain many of the layer's properties, including its remarkably low friction. I believe the problem has been completely resolved, says Sun. Most in the ice field are not convinced. Jen Sasaki at Hokkaido University in Sapporo, Japan, who made the first direct observations of this layer in 2013, prefers to call it a quasi-liquid. He thinks it represents a transitional stage between solid and liquid as the temperature goes up. For Sasaki, understanding how this mysterious sheet of H2O forms is still some way off. Even when it comes to something as familiar as slipping on ice, he says, reality is much more complicated than we expected. Clearly. The next one is, what is glass? Another random one. Are any of these surprising you guys? Things aren't as clear as you might think. Glass is a weird kind of solid liquid, and how it comes to be like that defies all explanation. Forget the hoary myths peddled by tour guides at old European churches and cathedrals. Medieval window panes are sometimes thicker at the bottom, not because of the slow flow of glass over centuries, but because of the uneven way molten glass was originally rolled into sheets in the Middle Ages. Glass is not a slow-moving liquid. It's a solid, albeit an odd one. It's called an amorphous solid because it lacks the ordered molecular structure of true solids, and yet its irregular structure is too rigid for it to qualify as a liquid. In fact, it would take 1 billion years for just one of the atoms in a pane of glass to shift it all. But not everything about glass is quite so clear. How it achieves the switch from liquid to amorphous solid, for one thing, has remained stubbornly opaque. When most materials go through this transition between liquid and solid states, their molecules instantly rearrange. In a liquid, the molecules are moving around freely, then snap, they are more or less locked into a tightly knit pattern. But the transition from the glass blower's red-hot liquid to the transparent solids we drink from and peer through doesn't work like that. Instead of a sudden change, the movement of molecules gradually slows as the temperature drops, retaining all of the structural disorder of a liquid, but acquiring the distinctive physical properties of a solid. In other words, in all forms of glass we see something unusual. The chaotic molecular arrangement of a liquid locked in place. The process underlying this strange behavior remains an open question. The number of explanations also matches the number of researchers, says Hajime Tanaka at the University of Tokyo in Japan. One possibility is that it's all down to energy use. According to the laws of thermodynamics, which govern how energy is transferred within a system, every collection of molecules is driven to find an arrangement with the lowest possible energy. But within any given system, some patches do better than others, meaning different groups of molecules settle into different configurations, and overall into an irreconcilably chaotic arrangement. But even if we put it down to thermodynamic laws, it's not clear what exactly drives glass's strange behavior. The push for low energy might be the prime mover. Then again, it could be the irrepressible tendency towards a maximum state of disorder. That's a perfectly plausible proposal, though it raises the troubling question of how ordered solids manage to survive. Tanaka is not giving up just yet. So far, crystallization and glass transition have been studied independently, he says. But Tanaka believes that glass may form in a manner not all that different from crystals, which have proved an easy target for analysis thanks to their repeating geometric structures. If he's right, maybe glass will finally become crystal clear. Here's a good one. Next one is, can we get energy from nothing? It depends what you mean by nothing. Ask a physicist about a vacuum, the very definition of nothingness for most of us, and they will tell you it is pulsing with activity. According to quantum theory, in a vacuum, wave-like fields are constantly fluctuating, producing particles and their antimatter equivalents that fizzle in and out of existence. So even in the depths of interstellar space, there is plenty going on in what we call zilch. This idea leads to some outlandish predictions. In 1948, the physicist Hendrik Casimir proposed that if you place two parallel metal plates close to each other in a vacuum, there will be more quantum electromagnetic fluctuations either side of the plates than between them. Their proximity limits the wavelength of fluctuations in that space, creating a force pushing the plates together. The phenomenon became known as the Casimir effect. It's a weakling force, but it has been detected. And more recently, physicists like Chris Wilson, now at the University of Waterloo in Canada, have tried to prove another eccentric prediction, that it is possible to use the effect to release latent energy. Instead of allowing the fluctuations to tug on the plates, you rapidly... I'm just going to move my leg. It's falling asleep. Instead of allowing the fluctuations to tug on the plates, you rapidly force the plates together to squeeze their wavelengths and force out photons. Trouble is, you can't accelerate even the tiniest mirror to the huge speeds required. So in 2011, Wilson and his colleagues tested the dynamical Casimir effect, as it's known, by using rapidly changing electrical currents to simulate the effect of minuscule mirrors whooshing together at a quarter of the speed of light. Sure enough, a pair of photons jumped out from the vacuum, energy, albeit a piffling amount, from thin air. You can think of it as being like the mirror has knocked the particle into existence, says Wilson. The experiment didn't produce energy overall, generating the currents required more than was produced. But harnessing the Casimir effect remains theoretically possible, and even a small success might go a long way. Engineering the inside surfaces of the mirrors to manipulate fluctuating fields in a different way can create an outward pressure that pushes two objects apart. This reverse Casimir effect could come in handy when making switches for nanoscale devices. For now, though, the build-up of an electric charge between moving parts swamps the effect. And that's the least of the caveats. Some physicists still refuse to believe that quantum fluctuations in a vacuum are real. Never mind the Casimir effect and its reversal. Wilson is now refining his experiments to answer the criticism that he simply produced heat energy as a result of the apparatus warming up. And if he can show that the particles generated are entangled as predicted by Casimir, that would provide the most convincing evidence yet that you really can get something from nothing. I'm not too sure I understood a lot of what I was just reading then, but that's why I'm not a scientist. I just closed it down. So what are we up to now? Got 4 left. Why does space have 3 dimensions? But does it? For anyone versed in modern theoretical physics, that's not such a silly question. I don't know any mathematical reason why 3-dimensional space is more consistent than any other number, says Leonard Susskind of Stanford University in California. Susskind is one of the founders of string theory, which is our best stab yet at a unified understanding of physics, and perhaps the best known model in which extra dimensions are found. One of string theory's peculiar features is that when applied to fewer than 9 spatial dimensions, the mathematics goes wild, predicting violent fluctuations that rip apart the very fabric of the universe. But extra dimensions do more than just save string theory's blushes. In a wider set of theories, gravity leaking into a higher space could explain why in our 3 dimensions it is so weak compared with other fundamental forces, and why the expansion of the universe is apparently accelerating. So perhaps the question becomes, why does space have 3 visible dimensions? One idea from string theory is that the universe started out as an infinitesimally small 9D ball of string, but only 3 strands unfurled in its subsequent headlong expansion, leaving the others tucked up tightly in every pixel of our 3D space. Or perhaps our 3D universe exists on one of many brains, membrane-like entities that float around in a larger, higher dimensional space. Lisa Randall of Harvard University and Andreas Karch of the University of Washington in Seattle have shown that brains colliding in such a space would tend to form 3D brains, an explanation of sorts for why we see a universe with 3 dimensions. That's brains like BRANES, not brains. Just in case you're wondering. If large other dimensions do exist, particles escaping into them might take energy from those we see. The Largest Hadron Collider has been looking for the signatures of missing energy, so far without success. Such failures rile Carlo Rovelli of the University of Aix-Marseille in France. The idea that space could have more than 3 dimensions was proposed more than half a century ago, and has delivered more disappointments than results, he says. So we're back to the more basic question, why only 3 dimensions? Perhaps because some aspect of our universe wouldn't work otherwise. The precise degree of quantum weirdness we observe seems only possible in 3D space, for instance, and Susskind points out that in any other number of dimensions, the electromagnetic and gravitational forces would have very different strengths. With fewer than 3 spatial dimensions, for example, gravity does not lead to attractive forces. Atoms, planets, and stars would not form properly, and humans would not be around to ponder the existence of dimensions. Did such a peculiar, curiosity-friendly 3D universe arise as part of a multiverse in which every possible type of universe exists? A possibility espoused by string theory? Or is it just one of a kind? That's a toughie, but either way, we're still a distance away from explaining the essential 3-ness of space, says Randall. I think it would be lovely to have an answer, but as of now we don't. Fair enough. This one's kind of interesting. Why do we move forwards in time? There is a reason we say time goes by. It seems to flow. No matter how still we stand in space, we move inexorably through time, dragged as if in a current. As we do, events steadily pass from the future via the present to the past. Isaac Newton saw this as a fundamental truth. All motions may be accelerated and retarded, but the flowing of absolute time is not liable to any change, he wrote. So how does time flow, and why always in the same direction? Many physicists will tell you that's a silly question. The idea that time can, in some meaningful sense, be said to flow is just a complete non-starter, says Hugh Price, a philosopher at the University of Cambridge. For time to flow, it must do so at some speed. But speed is measured as a change over time. So how fast does time flow? George Ellis, a cosmologist from the University of Cape Town, South Africa, has an answer. 1 second per second. Price says that's meaningless. Even if time was standing still, It could be said that for every second that passes, 1 second passes. Indeed, if that's a measure of flow, we could say that space flows. It passes at 1 meter per meter. Ellis is up against one of the most successful theories in physics, special relativity. It revealed that there's no such thing as objective simultaneity. Although you might have seen 3 things happen in a particular order, A, then B, then C, someone moving at a different velocity could have seen it a different way. C, then B, then A. In other words, without simultaneity, there's no way of specifying what things happened now, and if not now, what is moving through time. Rescuing an object now is a daunting task, but Lee Smolin of the Perimeter Institute of Theoretical Physics in Waterloo, Canada, has given it a go by tweaking relativity. He argues that we can rewrite physics in a way that includes now if we sacrifice some of our objective notions of space. Most physicists aren't having it. The general consensus is that time is more or less just like space, an immutable dimension stretched out through a 4-dimensional block universe. Every moment in that universe has a past, present, and future, says Sean Carroll from the California Institute of Technology in Pasadena. A person is described as a history of moments, and those moments all have a feeling that they're moving from the past to the future. That doesn't answer the question so much as shift it. If time does not flow, what makes us think it does? And then mystery number 9. This is going to be a weird one, I'm sure. Where does quantum weirdness end? In the bizarre reality of the quantum world, particles can be in 2 places at once. Why can't golf balls or milk do the same? Right? We do not find at breakfast that the milk is simultaneously poured onto our cornflakes and not, says Andrew Briggs, a physicist at the University of Oxford. Nor can you be in 2 places at the same time, no matter how hard you try, none of which is even remotely surprising. Until that is, you consider that the laws of quantum mechanics insist that subatomic particles such as electrons routinely pull off such a feat. So if electrons can pop up in multiple places at once, why can't milk and humans, essentially collections of fundamental particles, do the same? Here we have to start small. This particular brand of quantum weirdness is best illustrated by the double-slit experiment, where you would fire a beam of electrons, one after another, at a screen containing 2 slits. You would expect the electrons to pass through one slit and hit the detector placed behind the screen at a single point every time. But reality isn't always that straightforward. When researchers don't keep track of each electron's path, the beam passes through both slits simultaneously in the same way as a light wave, creating a pattern of bright and dark stripes on the detector that is characteristic of 2 overlapping wavefronts. So electrons can exist as both waves and particles at the same time, a phenomenon known as wave-particle duality. As if that wasn't weird enough, when researchers monitor one of the slits, the interference pattern disappears. Electrons suddenly abandon their wave-like behavior, preferring to travel through one slit and produce a single spot on the detector. That's probably always the weirdest part of quantum physics, is like things change when they're observed. Physicists explain this by invoking the wave function, a mathematical widget that describes the probability of finding a quantum object in a particular state or location at any given time. When the particle is measured or disturbed in some way, its wave function collapses and it snaps into a single state and a definite position. This collapse can be triggered by an interaction of a quantum object with its environment, a rogue vibration for example, or heat fluctuation. That leads us to an unsettling conclusion. Isolate a molecule even hundreds of thousands of times the size of an electron sufficiently from its environment, and there's a chance it might still be existing in its uncollapsed quantum state. Indeed, researchers have now spotted improbably large objects, including tiny resonating strips of metal visible to the naked eye, existing in two states at once. Even so, it's pretty clear that once something gets large enough, it throws off its quantum properties. As Erwin Schrödinger noted, it's absurd to say a cat can be both dead and alive. So how large can quantum weirdness go? Do you know the Schrödinger cat experiment? Some physicists would say that the size limit depends on the size of your checkbook, says Briggs. With a sufficiently sophisticated experiment, he argues, researchers could reliably screen out disturbances from the environment ever more finely to show ever large objects obeying quantum rules. Together with colleagues at Oxford, Briggs is testing the limits of quantum behavior more rigorously than any experiment to date. The challenge is to find ways to place bigger things in fuzzy quantum states that are less sensitive to outside influences. But Briggs does not expect to solve the conundrum anytime soon. That's partly down to the difficulty of defining a system in quantum mechanics. Strictly speaking, anyone or anything observing quantum interference becomes part of the system, making it tough to draw conclusions about the size at which quantum effects vanish. You can always argue that you, the observer, are in superposition too, says Briggs. And lastly, this one relates to all of us, really. The last one is how creative computers will dream up things we'd never imagine. On a summer's day in 1899, a bicycle mechanic in Dayton, Ohio, slid a new inner tube out of its box and handed it to a customer. The pair chatted and the mechanic toyed idly with the empty box, twisting it back and forth. As he did so, he noticed the way the top of the box distorted in a smooth spiral curve. It was a trivial observation, but one that would change the world. The shape of the box just happened to remind the mechanic of a pigeon's wing in flight. Watching that box flex in his hands, Wilbur Wright saw how simply twisting the frame supporting a biplane's wings would give him a way to control an aircraft in the air. Serendipity and invention go hand in hand. The Wright brothers' plane is just one of many examples. Take Velcro. George de Mestral invented the material after he noticed the hook-covered seeds of the burdock plant sticking to his dog. And Harry Cooper's liquid plastic concoction failed miserably as a material for cockpit canopies, as it stuck to everything. But it had a better use, superglue. It may be romantic, but it's an achingly slow way to advance technology. Relying on happenstance means inventions that could be made today might not appear for years. The way inventions are created is hugely archaic and inefficient, says Julian Nolan, CEO of Iprova, a company based in Switzerland which specializes in generating inventions. Nothing has changed for hundreds of years, he says. That's totally out of sync with most other industries. But we are starting to make our own luck. Those eureka moments could soon be dialed up on demand as leaps of imagination are replaced by the steady steps of software. From algorithms that mimic nature's way of producing the best designs to systems that look for gaps between existing patented technologies that new designs might fill, computer-assisted invention is here. The impact could be huge. Some claim automated invention will speed up technological progress. It could also level the playing field, making inventors of us all. But what happens if the currency of ideas is devalued? To qualify for a patent, for example, an idea can't be obvious. How does that apply when ideas are found by brute force? The first group to mimic evolution in pattern design, pioneering the use of so-called genetic algorithms, was led by John Kosa at Stanford University in California in the 90s. The team tested their algorithms by seeing if they could reinvent some of the staples of electronic design. The early filters, amplifiers, and feedback control system developed at Bell Labs in the 20s and 30s. They succeeded. We were able to reinvent all of the classic Bell Labs circuits, says Kosa. Had these techniques been around at the time, the circuits could have been created by genetic algorithms. In case that was a fluke, the team tried the same trick with 6 patented eyepiece lens arrangements used in various optical devices. The algorithm not only reproduced all the optical systems, but in some cases improved on the originals in ways that could be patented. Just looking through this article, it's really long. I'm going to skip ahead a little bit because I don't think it even really matters. Let's get to the point, Human inventors who use automated innovation will leapfrog those who don't. But where do we draw the line between the two? I don't think there is a clear separation between human and algorithm, says Eric Bonobo, founder of Ecosystem, a company based in Cambridge, Massachusetts. The key is to find the right division of labor. Ecosystem uses genetic algorithms to optimize everything from inventions to business processes, an approach Bonobo calls enhanced serendipity. However, if the division of labor is too much on the computer's side, it could undermine the patent system itself. Currently, a person having ordinary skill in the art must believe that an invention isn't obvious if it is to be granted a patent. But if inventors are only tending a computer, the inventions that arise could be deemed an obvious output of that computer, like hot water from a kettle. These concerns have already been raised with drug discovery. If drug discovery tools become so powerful that a researcher is just overseeing the tool's activity, does that make the whole process obvious and so not patentable? Industry could be shooting itself in the foot by developing such technology. Another concern is that broad access to smart invention tools could speed up human technological development, making the resulting gadgets may consume Earth's resources all the quicker. McCaffrey is more optimistic. I'm really impressed with the engineers who are creating ways to improve housing, food storage, crop growth, water purification, and transportation in the developing world, he says. I sincerely hope we use this emerging invention assistance technology to address the really important problems faced by humanity. Chance favors the prepared mind. If Wilbur Wright hadn't been thinking about his problem, he may never have had his eureka moment. Automating that amounts to making accidental encounters orders of magnitude more efficient, says Bonobo. In other words, outsource serendipity to the algorithm. Anyway, that is the end, guys. Some of those were a bit easier to understand than others, weren't they? But then not really at the same time. Take something as simple as ice being slippery and then have a big discussion about why. Anyway, I will keep looking through this website over the coming weeks and see if I can find some other interesting ones to read to you. So I hope that you'll like that. And thanks for watching, guys, and hello to all the new subscribers that have signed up recently. And I will see you guys in the next video. Bye.